Hello everyone, in this discussion we'll talk about how to compute the summary effect using random effect modeling, and we'll discuss three examples, three worked examples. So one example will be a meta-analysis using studies which report continuous data, one will be using studies which report binary data, and one will be using studies that report correlation coefficients, and we'll be computing the summary effect as well as the p-values for testing the null hypothesis using random effect modeling. So the steps involved in random effect modeling are very similar to the steps involved in fixed effect modeling. The most important difference is with respect to how we compute the study weight. The study weights, I'll talk about this in detail further, but the study weight in fixed effect modeling is the reciprocal of the within study variance, whereas in random effect modeling the study weight of any given study is the reciprocal of total variance, which is the sum of within study variance as well as between study variance. So the only extra step really that you have to perform in random effect modeling is computing the between study variance also. You cannot just rely on within study variance, you also have to compute between study variance, then only you will distribute the effects, and then you can compute your summary effect. Rest of these steps are exactly the same as was in fixed effect modeling. So the first step, we'll go step by step. We know that the first step will always be computing the common effect size index for all the individual studies. Now if the study is reporting continuous data, it could be raw mean difference or unstandardized mean difference or standardized mean difference, which could be Cohen's d or Hedges g, or it could be response ratio also. Remember that if you are using any ratio, then it has to be converted into the logarithmic form to perform the calculations of the summary effect as well as p-values. Then and did not discuss why in the previous lecture. I'll try to discuss at the end of this lecture why we have to convert the ratios into the logarithmic form before computing the summary effects in fixed as well as random effect modeling. And let's say the studies are reporting binary data. In that case you can use something called as odds ratio or relative risk or risk difference. Again, because these are ratios, you have to convert them into logarithmic form before you compute the summary effect. If the study reports something called as correlation coefficient, then you can convert it into Fisher Z. The reason you have to convert it into Fisher Z is because the variance of the correlation coefficient is actually dependent a lot on the correlation coefficient itself. So it is preferred by most authors to convert the correlation coefficient into Fisher Z before doing all the computations for the summary effect. So this is the first step. We'll compute a common effect size index for all the individual studies. Then of course you will compute the variance associated with this effect size, that will be the within study variance. And this was the only variance that was important in fixed effect modeling, but in random effect modeling we'll compute one more variance, which will be the between study variance. And of course then you'll convert this variance into standard. You can also compute the standard error for each study. And then one more variance you have to compute when you are doing random effect modeling will be the between study variance, which we will denote by t square in this discussion. So there are several methods of computing the between study variance. The method that we'll be using in our examples today, this will be the Dar-Simonian and Laird method. So this is how we compute the between study variance using this method. The formula is q minus degree of freedom divided by c. So what is q? Q is the summation of wy square. W will be the weights of the study based on fixed effect modeling. So first we'll assign the weights according to this formula. Weight is the reciprocal of the within study variance. So this is the same formula that we use in fixed effect modeling, right? So first we'll compute the weights of the study based on this formula, and this is the W that we will use for computing the Q. Y is obviously the effect size of the individual study, and we'll compute wy square. This will become clear as we go through the examples. So you'll compute this product wy square, and then you will sum up the wy square for all the studies. This minus sum of wy to the whole square divided by summation of all the study weights. So remember, the most important thing you need to remember is this W is the same weight as what you compute in the fixed effect modeling. So it is the inverse of the within study variance. Degree of freedom is obviously number of studies minus 1. C is the summation of the weights of the study minus summation of the weight square divided by summation of weights. So this, how to use this formula, it will become more clear as we go through the examples. So first you compute the common effect size index, you compute the study variance, within study variance, then you also compute the between study variance using this method. After that you have to compute the weight of each study as per the random effect modeling. So you know that and in this case, in this discussion, we'll denote the weight of the study as per random effect modeling with W star. So remember, this W is not the same as this W. This W will represent the weight as given in fixed effect modeling. So it is simply the inverse of the within study variance, whereas this W is the weight which is assigned in a random effect modeling. So it is the inverse. So it is the inverse of. So this W star is actually the weight that we calculate in random effect modeling as per random effect modeling, and this is different. This is the inverse of the within study variance as well as between study variance. So please note this difference of W and W star. Okay, so then you have to compute the W star, because now that you know the between study variance, you can compute the W star, because now you have within study variance also and between study variance also. So now this is the main weight that is given. This is the main weight that we want to know basically for random effect modeling. And to know this W star, you need two things. You need between study variance also and within study variance also. And for between study variance, we use this formula, right? So now that you have assigned weights to your individual studies in random effect modeling, you can now go on to calculate the summary effect, which is nothing but the weighted mean of the individual studies. So the summary effect, for it could be summary anything. It could be summary raw mean index, summary Hedges Cohen's d, Hedges g, summary logarithmic response ratio, summary logarithmic odds ratio, or logarithmic risk ratio, risk difference, summary Fisher z. So it could be anything. The formula will remain same. It will be the summation of the product of the weight of the study and the effect size divided by the summation of the weights of weight of all the studies. But remember, this W is different, right? Because the weight, this W is not the same W as was in fixed effect modeling. That W was represented by simple W, and that was the inverse of the within study variance. But here the W is W star, and this is the inverse of the summation of total variance, which is the within study variance as well as the between study variance. So this W is on the main difference. Basically, this how we assign weights to the study, that is the main difference between fixed and random effect modeling. Everything else will remain same. So now you have the summary effect, then you can compute the variance of the summary effect. It will be inverse of the weight assigned to the studies in random effect modeling. Then you can compute the standard error of the summary effect. Obviously it will be under root of the variance. Then you can compute the lower limit and upper limit of this summary effect. So the lower limit will be summary effect minus 1.96 into standard error of the summary effect, and upper limit will be summary effect plus 1.96 into standard error of the summary effect. Finally, you can compute the Z statistic. That will be the summary effect size, whatever you have computed, divided by the standard error of this summary effect. Remember, if you are using a ratio, then it still has to be in the logarithmic form. So the summary effect is still in the logarithmic form until we calculate the p-values. Everything will be in the logarithmic form, and if it is correlation coefficient, then everything will be in the Fisher Z form only until we calculate the p-values. So then you have your Z statistic. After you have your Z statistic, you can calculate the p-values. One-tailed p-value, if you made the prediction in the right direction, will be 1 minus normal distribution function of Z, whereas if you made the prediction in the opposite direction, the p-value will be 1 minus normal distribution of minus Z, not Z but minus Z. Two-tailed p-value will be exactly twice of this one-tailed p-value when we made the prediction in the right direction. So it will be 2 multiplied by 1 minus normal distribution function of Z statistic. And of course, at the end, if your summary effect was in the logarithmic form or it was in Fisher-Z form, then you might have to convert them back into the exponential form and this Fisher-Z back into the correlation coefficient form to report the final summary effect and the upper and the lower limit. But for calculating p-values, everything has to be in the logarithmic or Fisher-Z form only. Okay, so now we'll see the examples. Hopefully these steps, they will make sense as we go through these examples. So first example is studies which report continuous data, and we will be computing Hedges G. This is the same set of studies that we took in examples of fixed effect modeling. I have already done fixed effect modeling for the same studies. You can go and watch that lecture and compare how the summary effect will be different in the two modeling. So the studies are, these are all the studies, 6 studies, and this is the mean effect that has been reported, this is the standard deviation, and this is the sample size of the treated group. Similarly, in this Carroll study, this is the control group, this is the mean of the control group, the standard deviation of the control group, and the sample size of the control group. So the first step is you have to calculate the Hedges G, of course, which is your effect size index that we have decided to compute in this case. So we know the formula for Hedges G. Will have to use this mean of group 1 minus mean of group 2 divided by SD within, and SD within will be sample size of group treated group minus 1 multiplied by standard deviation of treated group square plus sample size of control group minus 1 multiplied by standard deviation of control group square divided by n1 plus n2 minus 2. So you have all the values with you. This will be the x1, this will be the x2, this will be s1, this will be s2, this will be n1, and this will be n2. So you can calculate, and similarly you can calculate the variance also and the standard error. So until now, until this step, we have calculated Cohen's d, right? And you know that Cohen's d is it actually overestimates the effect size. So we sometimes decide to do correction in the Cohen's d and calculate Hedges G. So we'll use the J correction factor. The J correction factor will be 1 minus 3 by 4 degree of freedom minus 1. This is the formula for degree of freedom. And then you can calculate the variance in G also. That will be J square into VD, and then you can calculate the standard error in Hedges G. So these are the formulas. Let me know in the comment section if you want me to make a separate video on formulas for all the different effect size index which are used in meta-analysis. So you can use this formula to compute these effect size index. So all these effect size, they are basically Hedges G, and they have been calculated using this raw data for each of the study. So these are all our Hedges G that we calculated for each of the study. This is the effect size. Similarly, this is the variance in the Hedges G, and that also you can compute based on the formulas that I just told you. Now first you will just like you were doing fixed effect modeling, you would compute the weight of the studies by reciprocating the within study variance. So until now the steps are we are doing exactly the same as we did in fixed effect modeling. Nothing is different. So then we are doing the reciprocal. So you will get all the weights. These are the weights, right? Now you know we want to compute the between study variance. Now that is what we need. So to do that, we'll need some more information. So first we will compute the product of the weight and effect size, this. So 0.095 into 30 for example. And we'll also need WY square. So that is the weight of the study multiplied by effect size square. So we'll compute WY square, and we'll also compute W square. Once we have this information, and you also need summation of these all these index. So weight ka summation, WY summation, summation of WY square, summation of W square. Once you have this information, you can now compute the between study variance. So we'll use that same formula that I told you. So see, this is Q. Q is summation of WY square. Can you see what is the summation of WY square? It is 53. So here we will put 53 minus summation of WY ka square. So what is summation of WY? Summation of WY is 101. So 101 square divided by summation of weights. You know what is summation of weights? It is 244. So here we will put 244. So this is how you will calculate Q. Then you want to have C. So C will be summation of W minus summation of W square divided by summation of W. So summation of W is 244. Summation of W square. So this is W square, and the summation of W squares is, sum of W squares is 13802. So here you will put 13802 divided by sum of the weights. So that is 244. And you know the degree of freedom is number of studies minus 1. So that will be 5. Once you have this information, you can put it in this formula and you will get the between study variance, which will come to be 0.037. So this is the T square, which is the between study variance. So now finally you have the you basically have, for each study you have a within study variance also. You can see these all are the within study variance, which will be obviously different for each study. Why? Because within study variance depends on the sample size, and you know some studies will have more sample size, some studies will have less sample size. Studies with more sample size tend to have less variance. For example, you can see here the Donat study. This study had the most sample size, right, 200, and the within study variance is actually least for this Donat study, right? You can see within study variance will come to be least for the Donat study because of the maximum sample size. So for each study the within study variance will be different. However, this is the between study variance, and this 0.037 is actually common for all the studies. So remember this, between study variance is same for all the studies. Okay, so now we can go on to do actual steps of the random effect modeling now that we have the between study variance. So again, these are all the studies that I have written. These are the effect size, again same, Hedges G, exactly the same as was in previous table. Then this is the within study variance, again same as I showed you in previous table. Now here I have also added between study variance, which is T square, and you know it is same for all the studies, right? Whereas within study variance is different for all the studies depending on the sample size. So now that you have within study variance as well as between study variance, you can compute the total variance, which is here, and you can do the reciprocal of this total variance to get the W star, which is the actual weight given in random effect modeling. So this is the most important thing which is different between random and fixed effect modeling. It is the actual weight of the study, right? So I just want to show you this concept. Can you see, for example, in Carroll, the weight of the study of the Carroll study is 14 here. That is W star. That is for random effect modeling. But for fixed effect modeling, the weight was 30. Okay, so you can see the weight of Carroll study has actually decreased from 30 to 14 when we shifted from fixed to random effect modeling. Similarly, you will see the largest study, which was the Donat study. The weight of the Donat study was actually 95. It was a very high weight in Donat study in fixed effect modeling, but in random effect modeling it has decreased to 20. So this is the concept that I've already explained in previous lecture, that when we move from fixed effect to random effect modeling, the weight of the larger studies will decrease, relative weight, and the relative weight of the smaller studies will increase. Smaller studies, they become more important as we move from fixed to random effect modeling, and larger studies, they become less important as we move from fixed to random effect modeling. And this happens because of simply this between study variance. Okay, as long as this between study variance is non-zero, it will sort of balance out the weights of the studies. So now that you have the W star, which is the weight of the study as per random effect modeling, you can calculate the product of the weight as well and the effect size index. So this multiplied by this, that you can compute for each study, right? Now rest of the steps are pretty similar. How to compute the summary effect? You know it is the summation of the weight in random effect modeling with the effect size divided by the summation of the weight. So the summation of the sum of WY is 32 here, and the sum of the W is 90 here. So this is your summary effect. Then you can calculate the variance in summary effect, which is nothing but the reciprocal of the sum of weight. So the sum of weight is 90. So the reciprocal of 90 will be this. Okay, and I have just put 90 here. It should be 90.284, but you get the point. Then after this, you can just convert this into standard error take under root of this, you will get standard error. Then you can calculate lower limit and upper limit of the summary effect. So the lower limit will be the summary effect, which is 0.382 minus 1.96 into standard error. Upper limit will be summary effect plus 1.96 into standard error. So these upper limits and lower limits you have now. Next step will be to calculate the Z statistic. This will be the summary effect divided by the standard error. Can you see the standard error? Yeah, here. So this is the summary effect divided by standard error. This is your Z statistic. The p-value will be 1 minus normal distribution function of Z statistic, and 2 tail p-value will be double of this basically. So this is the final results that we have got after doing this random effect meta-analysis. The standardized mean difference, or Hedges G, was 0.36, right? This right here, this is 0.36. The 95% confidence interval is from 0.15 to 0.56, right? The Z statistic was 3.40. One tail p-value is this and two tail p-value is this, and this you can summarize in the form of a forest plot as well. Remember, these are this is nothing but the standardized difference, or the Y, that is being written. So you can see, I can just show you. These are all the Y's, 0.095, 0.277, right? So these are all the effect size, and this is the relative weight. So here they have converted the weights into percentage. So for example, the relative weight of the first study would be 14 divided by 90 into 100. For second study also 14 divided by 90 into 100. Third study will be 11 divided by 90 into 100. So these are the relative weights as per random effect modeling, and this is the forest plot. Okay, and this is your summary effect, 0.36. So this is the forest plot for this first example. Okay, now we'll move to second example, which is the example of a binary data. So in this case, we have events and non-events. You can take this into maybe event could be death or MACE events, kidney failure, whatever, metastasis. So there are events and then there are non-events. We have 1, 2, 3, 4, 5, 6. Again, we have 6 studies, and we'll do a random effect modeling for this example. So the first step, here we are doing, we have decided to compute odds ratio for all the studies. So it's pretty straightforward. You know how to calculate odds ratio. So I'll show you for first study, for the Saint wala study, it will be 12 divided by 53 divided by 16 divided by 49. So it will be 12 by 53 into 16 by 49. So that will be the odds ratio of first study. Similarly, you can calculate odds ratio for all the studies, right? But remember, as I've told you before, whenever we have any ratio, we have to do all the calculations in the logarithmic form. So here in this table, you will not see odds ratio, rather you will see the natural logarithmic of the odds ratio. So I will take the natural logarithmic of this odds ratio, and that I will write in this table. So you have all the natural logarithmic of odds ratio written here. Then you will also calculate the variance in the natural logarithmic of odds ratio, and the formula for this variance in natural logarithmic of odds ratio is actually 1 by 12 events plus 1 by 53 plus 1 by 16 plus 1 by 49. So this is simply the formula for variance in natural logarithmic of odds ratio. This also you can calculate for each of the study. Then in a fixed effect modeling, the weight is the reciprocal of the variance. So we'll take reciprocal of all of these variance. These are all the within study variance, and then we'll get the weights. Then you can calculate the product of W and Y to get WY square and W square, and you will also get the sum of them. So now you are ready to compute your between study variance. So again, you can see, to compute the between study variance, we are using the same LARD formula. You can see Q minus degree of freedom by C. Q will be sum of W Y square. Sum of W Y square is 32 minus sum of W Y. W Y is minus 30. So it will be minus 30 square divided by sum of W. W ka sum is 42. So divided by 42. Similarly, you have to calculate C. C will be sum of W. Sum of W is 42 minus sum of W square. So W square sum is 428 divided by sum of W. Sum of W is again 42. So there you have 42, and degree of freedom is number of studies minus 1. So then you can put them all into this formula to get your between study variance, which will be 0.17. So now that you have your between study variance, you are ready to compute the weight under random effect modeling. So this is nothing but the formulas of odds ratio and variance in the natural logarithmic of odds ratio that I've already told you. So now we are ready to perform the random effect modeling. Again, these are the same effect size as I was showing you in previous table. This is nothing but natural logarithmic of odds ratio. This is the variance in the natural logarithmic of odds ratio, or within study variance. Now this is between study variance that we just calculated, t square, and it will be same for all the studies, and within study variance will be different for all the studies depending on the sample size of the study. Then this is the total variance, which is the summation of within and between study variance. Then you can do reciprocal of this total variance to get the weight under random effect modeling, right? So these are the weights under random effect modeling, and finally you can calculate the product of the weight and the effect size, right? So now you are ready to compute the summary effect. So summary effect will be the product of weight and effect size, sum of product of weight and effect size divided by the sum of the weight. So it will be minus 0.99928 divided by 17. So this is the summary effect in terms of logarithm. This is still in logarithmic form, right? And then you can calculate the variance of the summary effect. It will be the reciprocal of sum of weight under random effect modeling. So it will be 1 by 17, right? So this is the variance. Then you can calculate standard error, just under root of this. Then lower limit and upper limit of the summary effect. So lower limit will be, you can see, summary effect minus 1.96 into standard error, whereas upper limit will be summary effect plus 1.96 into standard error. Then a z statistic, that will be the summary effect divided by standard error of the summary effect. So this is the summary effect and this is the standard error of the summary effect. So now you have your z statistic. Then you can calculate the p values. Again, p of 1 minus normal distribution of z statistic. Okay, this will be actually converted to this like this. Okay, so this minus will go away. So you just need normal distribution of 2.3711. Then two tail p value will be 1 minus normal distribution function of again 2.3711. So you will notice that this p value will be double of this p value actually. Okay, and finally at the end, because everything was in natural logarithmic form, to report the summary effect in the actual form, you can convert back it into exponential form. So odds ratio will be exponential of natural logarithmic of odds ratio. So natural logarithmic of odds ratio was minus 0.5663. So you will take exponent of that, and this is the actual odds ratio. The lower limit will be exponent of lower limit of the natural logarithmic of odds ratio. So here was the natural lower limit of the natural logarithmic odds ratio, that was minus 1.03. So you will take exponential of minus 1.03. Similarly, you will report the upper limit in the conventional form only. So finally you have the summary odds ratio here, the lower limit and the upper limit of the summary odds ratio. The z value, the z statistic you have, which was minus 2.37. p values are this and this, and you can make a forest plot now. So again, all of this is in the conventional form only. This is not the natural logarithmic form. This is actually exponential form, because it is just more interpretable to show the original form of the odds ratio, that has some meaning to it, whereas reporting the natural logarithmic of odds ratio may not make sense. So that is why we have converted the summary effect back into the original conventional form. Okay, and the relative weights as per the random effect modeling, again you know how to calculate this. So it will be, for example, for first study it will be 2.793 divided by 17 multiplied by 100. So like that you can calculate relative weights. So this is the forest plot for this study. Now we'll take one more third example, the last example, which is studies which are reporting the correlation data. So let's say we have these 6 studies, they are reporting this correlation coefficient, and this is the sample size for each of the studies. Now we know for correlation coefficient, every calculation, all the calculations till p value computation, they have to be done in the Fisher Z form. Usually that's what authors prefer. So again we'll compute Fisher Z for each of the study, and the formula for Fisher Z is 0.5 into natural logarithmic of 1 plus correlation coefficient divided by 1 minus correlation coefficient. So for first study, correlation coefficient is 0.5. So for first study, Fisher Z will be 0.5 into natural logarithmic of 1 plus 0.5 divided by 1 minus 0.5. So like that you can calculate Fisher Z. You can also so these are all the Fisher Z for all these 6 studies. Then you can also calculate the variance within study. Variance will be 1 divided by n minus 3. So for example, for first study it will be 1 divided by 40 minus 3. So you can see how much that is. That will be 1 divided by 37, right? So it will come to be 0.0270. So like that you can calculate within study variance. And now that you have within study variance, you can calculate the weights as per fixed effect modeling. So just by doing reciprocal of this, you will get the weights, okay, as per fixed effect modeling. Then you can compute the wy square and w square, and you can get the sum of each of these values. Now you are ready to compute your between study variance, which is the t square, right? I hope by now you know how to do this. You can pause the video. I have put it like this. You can just pause and see if you can calculate. So the wy square sum, it will be 127. The sum of wy here 242 square divided by sum of w, so that is sum of w is 647. For C you need sum of w, that is 647, minus sum of w square. So w square sum is 172,489 divided by sum of w is 647. And what is degree of freedom? It is 5. Number of studies minus 1. So now you can put everything into this and you will get the between study variance 0.0819, which is same for all the studies. So here again same, this table, these are all the Fisher Z. This is the variance within, this is the variance between, a t square, which is same for all the studies. This is the total variance. When you will do reciprocal of this, you will get the weight as per the random effect modeling, right? So this is the most important difference between fixed and random effect modeling. The weight assigned to the individual studies, it changes. So you can see the weight of Fonda study was 11 in fixed effect modeling, but in random effect modeling the weight has changed to 9. And finally you can also compute the product of the weight as per random effect modeling and the effect size. So this is the sum of that, okay? So now you are ready to compute the summary Fisher Z. So summary Fisher Z will be the sum of this weight wy divided by the sum of the weights, which is 59. So this is your summary Fisher Z. Then you need to compute the variance in summary Fisher Z, which is nothing but the reciprocal of the sum of the weights. So it is 1 by 59, and here you get the variance. So after this variance, you can calculate the standard error of the summary effect, which is nothing but under root, the lower limit, which is summary effect minus 1.96 into standard error, and upper limit summary effect plus 1.96 into standard error. Everything is still in Fisher Z form, okay? This Z statistic also summary effect divided by standard error. So this is the summary effect, summary Fisher Z 0.5328, and the standard error, which is 0.1298. Now that you have Fisher Z, you can calculate p-values, 1 minus normal distribution function of Z, and 2 into 1 minus normal distribution function of 4.1045. So these are the p-values. So until this point everything is in the Fisher Z form. Now because everything is completed now, before reporting the results, you will have to convert the summary data back into the correlation metric. So this is the formula that we use for converting it back. So the correlation coefficient is actually e exponential 2z minus 1 divided by e to the power of 2z plus 1, where z is the Fisher Z. So this was the summary Fisher Z, you remember, and you will put this into formula and you will get the summary correlation coefficient. Similarly, for lower limit and upper limit also, you will use the same formula exactly to convert the lower limits and upper limits also into the correlation metric form. So this is the final result of our meta-analysis. The final summary effect is 0.49. 95% confidence interval, lower limit is this, upper limit is this. The Z statistic, the Z value was 4.1045, and these are the p values. And you can also show this in the form of a forest plot. All of this is the correlation metric. We are not reporting Fisher-Z metric in the forest plot because it is not as easily interpretable for most people as correlation, right, coefficient obviously. So everything is in the correlation coefficient form, in the summary effect also in the correlation coefficient form. These are the relative weights as per the random effect modeling, right? And this is the forest plot and this is the summary correlation coefficient. So that's how you perform random effect modeling using I've shown three types of studies. First was studies reporting continuous outcomes, second was studies reporting binary data, and third was studies reporting correlation coefficient data. So now just a short note on why we have to convert the ratios into the logarithmic form. So you can understand why we do this by taking this example. Let's say you have two studies, study 1 and study 2, and for first study, let's say the risk in treatment group is twice the risk in control group. For second study, the risk in treatment group is half that of control group. Okay, let's imagine the risk ratio for study 1 was 0.50 and for study 2 it is 2. So it is exactly opposite, right? You can see in first study the risk in treatment group is half, but in second study the risk in treatment group is double. So you would expect that when you do a meta-analysis of these two studies, provided they have exactly same sample size, it should cancel each other out and the final risk ratio should be 1. That is what you expect normally to happen, right? So that is the expectation of symmetry, that if in one study the treatment group showing half risk, in other study the treatment group is showing double risk, so altogether the meta-analysis should say the treatment group risk is same as that of control group, right, provided both are same sample size. So what happens if we don't convert this into logarithmic form? Then the mean would be 1.25. What is the mean of 0.5 and 2? It is 1.25, right? If you were to compute the summary effect using non-logarithmic form of the risk ratio, the summary risk ratio you will get will be 1.25. This is obviously problematic. You don't want that. You want 1. So that is why we use the logarithmic form. Imagine you convert these two values into the logarithmic form. So the logarithmic of 0.5 will be minus 0.693 and for 2 will be plus 6.93. So when we combine them, mean will be 0. And when you convert this back into the exponential form, it will be 1, right? So this is the reason why we convert these ratios into logarithmic form before doing all the computations for summary effect and p-values and z statistic, because it just maintains the symmetry. It is needed to maintain the symmetry in the analysis. Okay.